Okay, I think 93 is a good number, Wendy.
Yeah, take it away.
Okay, so I'm Susan Margulies, and I'm the chair of the Wallace H. Coulter Department of Biomedical Engineering. It's my delight to welcome you here. Wendy's a tough one. Wendy, when we talked about how to celebrate her at this moment, she actually did a Wendy. She actually didn't reply to the request for feedback. But then even in COVID, when I texted her and said, "Are you in the building?" And she said, "Yes, I am." And we literally had a masked meeting in my office. And I posed to her the idea of creating a Newsteader distinguished lecture and to have her be the inaugural lecture. And she loved it immediately. So here we are. So with Wendy's approval. So I'd like to give a little bit of a bio about Wendy and how this lecture came to be, and literally present to her the plaque, which she will have, and there'll be a one in the office as well. And then I'll transfer the baton, if you will, or the mic to Don Giddens to talk a little bit about Wendy. So mine will be more factual, and Don will provide a little more context. So Wendy has been at Georgia Tech for a very long time, and it's a thrill to have her here. So Wendy, you actually joined in the College of Computing in 1996, I have from your CV. And that's after getting your bachelor's in Asian Studies from Colby College, your master's in Linguistics for Language Teaching from Lancaster University in England, and a PhD in Linguistics. And what I really want to share with people is that you are the author of 71 papers. And the scope of the papers that you've, and journal articles and conference proceedings are impressive. They include the science of learning, laboratory design, inclusive learning, interdisciplinary learning, integrative problem solving, cognitive partnerships, which is important in teams where members of the team come from different disciplines, learning assessments, cross-cultural translation of pedagogical methods, and the design of learning spaces. And you're coming out with papers still as we speak about women in makerspaces and other topics. So it's been a rich, exciting, and not yet concluded record of your deep engagement in the science of engineering pedagogy. And as a result of that mindset of research, you've actually won a number of awards. And so I'm just going to highlight a couple here. So you won an award for teaching, not surprisingly, the 1969 Teaching Scholar Award in 2008 and 9. You won a Center for Engineering, Teaching and Learning, or CETL Curriculum Innovation Award. And the one that I found interesting and had to look up a little bit more about is the American Psychological Association William James Book Award. And that was in 2012 for a book that you co-authored called The Agile Mind, which I have now ordered from Amazon. In 2019, you were awarded the National Academy of Engineering Bernard M. Gordon Prize for fusing problem-driven engineering education with learning sciences principles to create a pioneering program that develops leaders in biomedical engineering. You shared that prize with 2 other faculty in biomedical engineering, and we're deeply proud of this accomplishment and actually truly recognition at the highest level for your accomplishments to date. Part of that Gordon Prize came to Georgia Tech, and I asked that that portion of the prize money go to the department. And I created an endowment with the permission of the 3 faculty that would fund innovative educational pilots, also dissemination in all its ways, including potentially holding national meetings where we would invite people to workshops at Georgia Tech and Emory to learn innovative pedagogical. So dissemination is really key. It's not just that we're doing wonderful things in BME at Georgia Tech and Emory, but it's that we are enthusiastic about sharing it with the world, not just through scholarly papers, but also through workshops. So with Wendy's permission, one of the aspects that we're going to create in terms of dissemination and recognition is the Newsteader Distinguished Lecture. So what I'm going to do is read for you from this plaque, which was engraved. It's a piece of granite. This one is going to Wendy, and others are, one more is going to the department. And this is a plaque that was made in our student shop, okay? And I'm going to read to you what it says. It says, "The Newsteader Distinguished Lecture is hereby awarded to Wendy Newstetter in recognition of distinguished scholarship in innovative engineering pedagogy and translation to practice. This award is presented annually in honor of Dr. Newstetter's local and national impact as an educator and scholar who has devoted her career to excellence in engineering education." And it's got today's date on it. And it's my thrill to now introduce Don Giddens, who's the first chair of biomedical engineering at Georgia Tech, as well as the dean of the College of Engineering at Georgia Tech, to give a perspective and really to introduce Wendy, our lecturer today. Don?
Well, thank you, Susan, and welcome to everybody. It looks like there are 117 participants right now, so that's an amazing turnout and an amazing tribute to Wendy and to her colleagues. So I'd like to make this a little bit personal, if that's okay with everyone's permission, and indulge me in just a little bit of background that actually goes a few years back before BME was formed. One of the things that Susan asked me was, why Wendy? And how did she come into the picture? Well, I believe it was 1995, when I was Dean of Engineering at Johns Hopkins, I had the honor to give a distinguished ASME lecture called the Thurston Lecture. And most people that got that honor talked about their research. I decided I would talk about something different. So I gave a lecture on engineering education in a rapidly changing world, useful axioms and theorems. And without belaboring all of the axioms and theorems, and I know most of you kind of get where this is coming from in a mathematical sense, I postulated a number of axioms that you just couldn't argue with, like passive learning is an oxymoron, or training and education are not synonymous, etc. And then I used that to develop several theorems, which of course I didn't prove. But I want to read you two of those. I'm looking over at my other screen. This was theorem 4, integrating research and design throughout the engineering curriculum improves motivation and learning. And theorem 5 was partnerships with learning scientists and other educators lead to better teaching and learning. I thought those fit Wendy when you fast forward. So this was on my mind when I came to Georgia Tech in 1997. We formed the BME department. We initially had 3 faculty members in the department. Of course, there were a lot of faculty members in bioengineering, and Ajit and Michelle LaPlaca and myself were the 3 faculty members. And so we were charged to build a department, a new department, and at that time, it wasn't always accepted, believe me, that biomedical engineering was a real academic discipline. And I could give another talk about some of those experiences. But at any rate, we had no faculty, we had to recruit faculty, we had to develop curriculum, both undergraduate and graduate. And so we started really looking around for help. And I've forgotten exactly how I became aware of a learning science, cognitive science group in the College of Computing. Wendy, of course, Nancy Nursesian, who's also in the virtual audience. And I got connected with them. And I thought, okay, I'm going to go back to that theorem that I postulated about partnerships with learning scientists and actually try to do something with that. So they came over to my office, probably wondering why in the world somebody in engineering was was asking them to sort of help out. But it was well received. Nancy and Wendy, I think, viewed this formation of BME and the opportunity to develop a curriculum totally from scratch was a real good experimental laboratory for them and for their theories and what they wanted to do. So it was just a mutually good thing to do. It was good for everybody. Ajit has often used the term that this group was charged to develop a curriculum from a blank sheet of paper. The only constraint was that it did have to be ABET accredited at the end of the day. So that really is how we got started with Wendy. Of course, as we recruited faculty, other faculty jumped in, were engaged. Part of the criteria when we were recruiting faculty was that they had to be really interested in engineering education from a modern learning science viewpoint, and they had to work with Wendy and Nancy and their colleagues. The other little anecdote that I think is useful from a historical perspective is that the stimulus at first for this was the National Science Foundation had put out a request for proposals in engineering education in bioengineering. And so since we were forming a department, Bob Narum, who sadly is not with us any longer, said, you have to go for one of these ERCs and try to compete for that. And so we did. We decided to do that. But we had to reach out to other institutions because NSF loves these big conglomerate centers and multiple participants and so forth. That also was a set of interesting experiences, which I'm sure Wendy and Nancy will remember. End of the day, we were not successful with the proposal. We didn't get it. And I've often said that was probably the best thing that ever happened to the department in the early stage, because using that as a catalyst, we were able to rope in our learning scientist colleagues. They became committed, and we didn't have all of the overhead in dealing with MIT and University of Washington and other places that would really, I think, have slowed down the innovation. So from that point forward, the infusion of learning science principles, of design throughout the curriculum, learning in groups, learning rather than teaching, or in addition to teaching, just became infused in the development of the curriculum. I had very little to do with that, other than saying, hey, here's some resources. We're high faculty, bless you, and please do a good job. It really was led by Wendy, Joe Ledoux, Paul Benkesser, Ajit, and other faculty that came on board. We were then successful in getting the Whitaker Leadership Award, which was based upon research, but was really based upon the undergraduate program insofar as education was concerned. Then we were successful in getting the Coulter grant, for which the department was named, and a number of other things that came along. So from basically nothing, not 3 faculty members, no curriculum, we ramped up pretty quickly. I had a building design along the way, which Wendy and her group had very much influence on, and things took off. Well, after that happened, I bailed out, went to be Dean of Engineering, because if things were going so well, I didn't want to mess it up. And it really took off. I think the Gordon Prize is just a testament to that. It was sort of the icing on the cake, but there were so many things that happened along the way. Infusion of these ideas to BME departments that were starting up across the country, as BME was now becoming known as, yes, it is a legitimate discipline. A number of engineering colleges, not Georgia Tech, but a number of engineering colleges were embracing the idea of academic departments in engineering education, not aerospace engineering or chemical engineering, but in engineering education. And so I think Wendy and her group and the department just really were at the leading edge of a revolution in engineering education. And I think the Gordon Prize recognized that. So there's a big legacy that Wendy has given us, and Wendy and her team. It's a local legacy, as Susan said. It's made a huge impact on Emory Georgia Tech BME department. It's also made a huge impact on BME education in general. And I think it's not just a local and a national influence, but of course there's an international influence as well. So Wendy was basically a consultant for the development of BME in Abu Dhabi. So it's a wonderful legacy, Wendy, that you have given us, that you continue to give us. I was lucky to be a part of it at the outset. It was one of the best decisions I've ever made in my life. And I want to congratulate you, all of your team, all the many faculty who have embraced what you were doing. And congratulations. And I'm very much looking forward to this inaugural Wendy Newstetter lecture.
Thank you, Don. I guess I will take it away. Let me get my screen up and running here. Does everyone see a beach where they wish they were right now?
I do not yet.
I see one, but I'm looking out my window.
I don't see your screen.
Okay, hold on. Let me do this again.
There we go.
Okay, do you see a beach now?
Wow.
Yes.
Yes. Yes. Okay, good. Okay. First of all, I am profoundly honored and humbled to receive this recognition by the Biomedical Engineering Department. I can't thank Susan and Dawn enough for this recognition. It means so much to me. It has been my privilege to work with some of the most creative, thoughtful, and ambitious people in the United States. And I'm talking about both our wonderful Georgia Tech students and faculty. In fact, most faculty would agree that the reason we come to work every day is because of our students. I don't know if Dawn recalls this exactly, but when we sat down in that meeting of his back in 1998 about this engineering research center that actually had a request for proposals that was very specific. It was going to be an ERC devoted to the design and development of educational technology in support of biomedical engineering informed by cognitive science. And we met Dawn, Nancy and I, we sat across the table with each other. And at our first meeting, Dawn graciously, but somewhat sheepishly, started the meeting by confiding that he did not know what cognitive science was. But we reassured him by saying we did not know what biomedical engineering was. And that was the start for me of a 22-year partnership. And for today's inaugural talk, I want to return to that question. What is cognitive science and how might it inform the future of this lecture series? Cognitive science is actually a collection, and as I will show, a convergence in many respects of 6 different disciplines. Linguistics, or the study of language, its development, its various forms or morphologies, and grammars with the subdisciplines of psycholinguistics, sociolinguistics, and more recently, computational linguistics. Next, we have anthropology, or the study of humans and culture, their values, their rituals, and what Clifford Geertz, one of the most famous anthropologists, defined as the interpretive procedures we use to make meaning and make sense of our everyday interactions. Next, we have a relative newcomer, neuroscience, or the study of the brain and its parts and functioning. Philosophy seeks answers to many of the most significant puzzles we face as humans. What is the nature of existence? What is reality? What are values? And for our purposes today, what is the nature of the mind and how is it organized? Psychology is also interested in the mind, but in associated behaviors that are quintessentially human. And those subfields, and there are many of them, include developmental psych, abnormal psych, and cognitive psychology, just to name a few. And finally, we have AI, or computer science. In many ways, the quest to replicate or even go beyond in a computer what the human mind can do. Now, as I noted earlier, these disciplines actually converge in sharing two important questions. The first is, what is the nature of knowledge? What does it mean to know? What form does it take? But the next question is, what is the nature of learning? How does one acquire that knowledge? How does the mind change? So let me show you how these two questions manifest in the different disciplines, starting with linguistics and what I am trained in and what I use personally for research and for meaning making myself. Noam Chomsky is perhaps the most famous and popularized linguist of this and even the previous century. While he is noted for his political views, what really brought him to the attention of the academic world was a simple question that he asked in the 1950s. How are we as humans able to produce novel sentences that we have never heard before? Now, the reason this question was important was because at that time, the behaviorists, with B.F. Skinner as their champion, espoused stimulus response as explaining all learning and disavowing any attempts to figure out what might be happening in the mind. Chomsky's answer to this question, which behaviorism could not answer, was to hypothesize that all languages contain similar structures and rules of a sort that he called a universal grammar, and that children acquire language the same way and without much effort, indicating that we're born wired with basic language acquisition possibilities in our brains. He later termed this the language acquisition device. Now, Chomsky, with others, has been credited with starting what has been called the cognitive revolution, where not what was happening in the mind became the focus of study rather than just looking at responses to stimuli outside of the mind. Moving on, but back in time to our next discipline, we have Lev Vygotsky, a psychologist who, like Chomsky, was interested in humans and language acquisition. Lev, in contrast to Chomsky, developed what he termed sociocultural theory of language. His method was to observe very young children in settings where they actually acquired language from their parents or from caretakers. What he noticed was that learning was mediated by others in the environment, caretakers, parents, other children, and that what happens first in the interpersonal space or realm then transforms into the intrapersonal in the mind. This means that the internal is crafted and molded by what happens externally. This proposal entailed the notion of scaffolding, where the caretaker or the parent or the competent language user interested in the many ways of the student and the learner and made it possible for the learning child to perform at a level otherwise not possible. Today, that notion of scaffolding is very, very important in how we think about the design of any kind of learning environment. Jean Lave, an anthropologist who studied everyday activities like shopping in supermarkets and tailoring in Africa, coined the term community of practice. She contended that to understand learning, it was important to understand that it is mediated by the desire to become a member of an existing community, whether it be the family, Weight Watchers, Alcoholics Anonymous, a research laboratory, or engineering as a discipline. And that these communities of practice have specific forms of participation. And as members, they develop forms of participation in that community that are valued. So newcomers or outsiders to that community are offered by members what Jean Lave called legitimate peripheral participation. This construction of learning has come to be known as situated learning, in that it always takes place in a context that is important to understand. Now we move to folks I know and that I have worked with at Georgia Tech. I start with Ashok Goel, an AI researcher who has had an eclectic career, starting with his early work on design cognition and whether it might be possible to understand the processes that human designers use and replicate those on the computer. He then built a system to support middle schoolers in developing systems thinking around ecosystems. And most recently, he became known for his work with IBM Watson and his teaching assistant, Jill, an AI artifact that could parse and then field questions from students in an online computer science class. Next is Nancy Nursesian, a longtime friend and close collaborator for more than 12 years, who began to ask questions that traditional philosophers eschewed. Trained as a physicist, she wanted to understand how Faraday and Maxwell were able to make their significant breakthroughs. In perusing Faraday's notebooks, she became intrigued with the sketches and notes present there. Other philosophers ignored these as unimportant, but she asked, what are all these visualizations doing in the technical scientific work, and what do they have to do with reasoning? Her answer has profoundly influenced how we understand the importance of these external provisional models in thinking, reasoning, and scientific breakthroughs. You might say she is actually the mother of model-based reasoning. And finally, we come to Steve Potter, who is on the call as well, and it was great to see him. A neuroscientist whose lab Nancy and I had the pleasure to study as cognitive scientists for 2 years. Steve was also interested in learning, not in the classroom or the psychology lab, but in a dish. A brain in a dish was his research platform, comprising 10,000 disassociated cortical rat neurons seated on a plate of multi-electrode arrays that were designed to capture the electrophysiological changes among the cells as they were stimulated or as they learned. A brain scientist targeting what he termed the meso level of brain activity. Now, all of these cognitive scientists have had a profound influence on how I have come to understand learning and cognition generally, but in engineering more specifically. Noam Chomsky, for example, opened me and my mind to the fact that there may be these internal structures that we as educators are actually trying to build. They aren't genetically programmed, but we are trying to build these internal structures that are generative for new forms of activity. Lev Vygotsky has been very influential in how I've thought about the design of classrooms. And he has this notion of what's called the zone of proximal development. And what that zone is, it's fairly limited if students don't have sufficient scaffolding to bring them up to a level that is much higher from where they are at this particular point. And for certain, in the design of the PBL classes, this notion of scaffolding has been incredibly important to figure out how do we have second year students operate at the level of possibly grad students. And the only way we can do that is by significant scaffolding. Now, Jean Lave's work on community of practices was extremely influential for me because I joined a community of practice, which was biomedical engineers, a tribe, a weird tribe, a strange tribe with strange practices that over time, Nancy and I began to understand in one way or another. Ashok Goel was very important to me early on in helping me understand design cognition and how design is the most complex of all problems we have to deal with, and the difficulty of supporting students in learning how to contend with the ill-structuredness and the open-endedness of design. Now, Nancy has been my mentor for the last 20 years. We have had many adventures together. We have fought, we have laughed hilariously, and we have actually discovered some very important things in the 12 years that we had the honor and pleasure to actually investigate research labs at Georgia Tech. And I saw Eberhard on the call. Bob Nerum was the first who generously said, yes, come and study our research lab. And we spent 2 years trying to understand how do people reason and problem solve, and what is the nature of cognition when you are on the frontiers of science trying to build tissue. We also studied Steve Potter's lab, and we were lucky enough to study also Melissa Kemp's lab. So all of these faculty members at Georgia Tech graciously allowed us to come as anthropologists, as cognitive scientists, as linguists, and ask a lot of questions. And finally, Steve had such a vision for the kinds of questions he wanted to do. His attempt to meld art and engineering resulted in art exhibitions that were in Ireland and also in Australia. So all of these folks have been monumentally important to me in how I think about the design of learning environments. But then I want to talk about what it was like to join the department back in 2000. Oliver Sacks wrote a book in 1995 titled An Anthropologist on Mars. He was a neurologist who worked for many, many years with very different kinds of patients. And you'll notice the subtitle of this is 7 Paradoxical Tales. Now, in this book, he recounts a number of cases that are highly improbable. In one case, there's a surgeon who has Tourette's syndrome, but somehow manages to use his scalpel with skill. In another case, or in another tale, there is a person who was born sighted, lost his sight for many, many decades, and regained his sight, but in the end was much happier being blind. In every single one of these cases, they are paradoxical because he, as a neurologist, discovered things that actually were really difficult to comprehend, but they told him something about the human mind. When I joined the department in 2000, I often felt like this anthropologist on Mars. And I want to share with you the first time this happened. We were trying to develop a problem-based learning curriculum with the inaugural class of PhD students, 7 women. And so the first problem we gave them what was actually a court case that one of our faculty members had been asked to testify in. It was a really tragic situation where a baby had died, and the question was, did one of these parents shake this baby to death? And we asked our 7 students to determine whether that happened or not. Now, on the day of the presentation, when the students presented their findings and what they thought, I looked around the room and I could tell the faculty were not happy. They were not happy with what the students were presenting. And of course, as an outsider, and I'm not an engineer, I've never taken any engineering courses, I'm curious. I'm an ethnographer. I'm wondering, why is everyone looking like they're unhappy with how the students have solved this problem? So I went to the faculty member who was who did testify in court. And I said to her, why didn't you like the way they tackled the problem? And she said, well, I wouldn't have done that way. And I said, well, what would you have done? And she said, well, I would have done a back of the envelope calculation. And I said, I don't know what that is. And I passed her a blank piece of paper and she drew this picture on it. A circle with some arrows at the top and some squiggly kind of thing at the bottom. And then she put F equals MA and she started to write a bunch of equations. So I'm watching this and I'm thinking either this person is idiosyncratically developing their own method of attacking problems. And as ethnographers, we're always concerned with what's called the fallacy of the ethnographic moment, which means you have mistakenly assumed that some kind of idiosyncratic practice is actually a vast cultural practice. So I had to go confirm this. And so the next day I went into another faculty's office who had never seen this problem. And I said, you know, there was this case and blah, 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 you know, and I passed him a sheet of paper and I said, if you were going to begin to think about and solve this problem, what would you do? And he reproduced the same graphic. And I'm saying to myself, this is a baby? So for me, this was my first introduction to engineers and how they constrain, idealize a very complex system into something like a ball, arrows, and a spring. And so this takes me back to what Clifford Geertz talked about in terms of explaining culture as a historically transmitted pattern of meanings embodied in symbols, a system of inherited conceptions expressed in symbolic forms, by means of which men communicate, perpetuate, and develop their knowledge about and their attitudes towards life. So, boy, there were a lot of symbols here. And when both of those engineers looked at the ball and the arrows and the spring, it had meaning to them. But for me as an outsider, it meant nothing. But another thing became really interesting to me as a linguist at that time, is it began to be clear to me that something was going on in terms of transformations, that there's a court case, is textual, it's written in English, it's got nouns and verbs and paragraphs. And somehow that whole text got transformed into some kind of ball with some arrows and a spring. And then that diagram was turned into mathematical equations. So for me as a linguist, this was very significant because what it meant is you had 3 different semiotic systems connected to, relating to, and moving through a kind of pattern of sorts. And so I got very interested in this notion of representational transformations. So what this really means is in one sense, the text, the court case, is a representation of the situation. The diagram is another very constrained, very idealized, very simplified representation of the same situation, and the math is another symbolic representation of the same system. So this became really interesting to me as a cognitive scientist, because then I'm asking questions like, so what are the cognitive demands? What kind of knowledge is necessary to move through these different semiotic systems? What kind of schemas, what kind of scripts need to be developed that allow people to transform a massive text into a ball and some arrows? How do they extract from the text? What are they looking for in the text? And then what is in the diagram? What are the cues? What are the notations? What are the cues of how to transform that picture into a mathematical equation? And then, of course, the real question is, how hard is this transformation to learn? And where are the issues in learning? Because this is what we're actually training our students to do. Now, Joe Ledoux and I had an NSF grant to actually study this. We were particularly interested in this first transformation. How do students move, or fail to move, in most cases, from a text to a diagram? Because students really struggle with that first step. So if we look at studies that are done on experts and novices, particularly in areas like physics, we see some of the resources that experts have that novices don't have for navigating this text to diagram to symbol transition. Experts have categories in their minds. So for example, in statics, you have roller problem types, you have pin problem types, you have multi-unit process types of problems, you have mass balance problems, you have energy balance problems. What experts do when they're faced with a problem is they try to categorize the problem type that they're facing. For me as a linguist, that would be an answer to the question of, what event type am I in? And if you don't know what event type you're in, if you don't have a set of categories in your mind that you've learned that you can fall back on, you can't even begin this process of problem solving. The next question is, given the event I'm in, the event type, what schema or what scripts are available for me to make cognitive moves that will take me through this problem? In other words, now that I know what event I'm in, what do I do now? And then there is this deep conceptual understanding for application. Experts have this deep conceptual understanding of mass, of temperature, of momentum, of equilibrium. And they know what concepts to call up and apply to a problem, which novices don't. They flounder and they are missing these deep conceptual tools. And then also, a novice, unlike an expert, doesn't have a lot of cases, a database of realistic problem scenarios and solutions that they can take advantage of analogically to apply to this new problem type. So there's massive difficulties in learning to think and reason and problem solve for students. So the engineering method is very challenging. And sadly, classroom pedagogy, by and large, focuses on solving problems and not on learning. Students import a math problem-solving strategy. In other words, you start with an initial state, you have a goal state, and then you have some operators, into engineering problem solving, which is missing a step, which is the diagrammatic reasoning or the modeling. So you've got epistemological dissonance here among many of our students. They practiced so many word problems that when you ask them to draw the statics diagram, the free body diagram, the circuit diagram, they look at you like, why would I do that? So there's this epistemological dissonance that actually happens for many years in engineering education. For novices, the cognitive load is so great at first of managing all of these kinds of decisions, trying to figure out categories, trying to figure out, is there a script, that they use means ends analysis, working backward from the goal and not forward like experts. This is a coping mechanism. And their attention gets focused on problem solving, so they lag in actually learning the categories, learning the schemas, and practicing applications of concepts or intentionally building cases. So what I'm trying to say is, strangely enough, solving a problem and acquiring a schema require largely unrelated processes. So the question is, how do we uncouple those? To acquire a schema, a learner must recognize a problem state as belonging to a particular category, requiring particular moves. In other words, this is the classification, this is the procedure. And a problem solver's cognitive processing capacity is focused on attaining goals, a solution, not on acquiring a schema. So we see over and over with students what faculty call plug and chug. And then problem solving impacts selective attention. In other words, we have only so much available attentive space in our brains. And if it's all focused on solving a problem and not on actually learning it, this becomes problematic later on. So recently, we are writing a paper at this point about something that someone talked about quite a bit, quite a long time ago, David Perkins, who's at the Harvard School of Education. And he mentioned in an article pretty quickly in passing, something that he referred to as troublesome knowledge. Now, when you look at that, you think, okay, what that means is it's something about the knowledge that is troublesome, but in fact, what it refers to is the kind of knowledge our students show up with in classes that is troublesome for us and for them. And he talks about 4 different kinds. The first is inert. So inert knowledge is knowledge that maybe students have memorized, but they can't transfer it. They can't apply it in new situations. It doesn't come up easily. It's very hard for them to retrieve it. It's just hanging there like a cobweb in the attic. Another form of troublesome knowledge, and faculty see this all the time, is ritualistic or routinized. This is plug and chug. This is where the students just plug in some kind of equation without any deep conceptual understanding of what the equation means or why it might be important at that particular time. Another form is conceptually wrong. Now, this is when students have, for one reason or another, arrived in the classrooms having supposedly learned something that was difficult, but they actually have it wrong. So there are many, many instances of this in physics and also in biology and chemistry, where students are coming to us with conceptually wrong ideas. And then finally, we have alien, and this has become very interesting to me recently. What Perkins meant by this kind of knowledge is that it forces the students to take a new perspective or to have a different mindset from anything they've experienced before, and they feel conflicted. So I have some theories about forms of alien knowledge that happen in engineering. And Joe and I have talked about this. And one of these is estimation. If you've ever asked students to estimate, they just want to run out of the room in the other direction. And the other one is coming up with assumptions. So when we begin to think about that, the question is, so how are students positioned differently when they're asked to estimate or when they're asked to come up with assumptions? They're positioned in a way where they're given certain rights, duties, and obligations they've never been given before as learners, where they were told the number or they were given the constraints. So this kind of knowledge, I think, is actually quite rampant in engineering and really has not been talked about. It's perspective taking of the kind that is demanded when engineers have to make judgments when they don't have all the information. So when students show up in classrooms and they can't seem to demonstrate that they have mastered what they were supposed to have mastered in previous courses, we suspect that it falls into one of these 4 kinds of categories. So then the question becomes, so what are we going to do about this? How do we solve this problem of troublesome knowledge? And I'm not going to answer that problem today, but I'm going to take us to another graphic, which is the learning sciences. Because I consider myself a learning scientist. And as a learning scientist, I would want to answer that question. How do we make sure that students don't develop knowledge that is inert, that is routinized or ritualized, that is conceptually wrong? And how do we apprentice them to forms of being in the world and forms of making knowledge that feel conflicting to them and require them to take on new personas and new ways of acting in the world? So the learning sciences comprise things we've already seen: cognitive science, linguistics, neuroscience, psychology, computer science, but we also have design studies at the very top, and we need many, many more of these. Design studies are when you, as an educator, do your homework and you try to understand to the best of your ability the optimal conditions for learning something. And then you put them into effect in a classroom through some kind of intervention. And then you collect data to determine whether your hypothesis about that particular design was accurate or not. And you iterate over time. Now, for those of you who are engineers and design engineers, this is just design. It's design studies where you actually implement, you prototype, you learn something, and you keep doing this iteratively until you optimize. And honestly, if you think about it, in education, in the design of learning practices, in learning environments, we face the same thing that engineers face. The best you can do is optimize. It's never going to be perfect. So I want to share one more graphic with you, because what I am doing here with these graphics is trying to present possibilities for how one would begin to think about future lectures. Some of you may have seen this already. This was a graphic from a report that came out of a workshop sponsored by NSF in 2013 that was really trying to excavate what are the competencies that we need in the 21st century for people to be successful. Now, if we look at the blue, the cognitive cloud, you could say that that's what the average engineering classroom is like. The average STEM classroom is like. You're building conceptual models in the learner. They're practicing problem solving. You are requiring them to think critically, analytically, make decisions, innovate. So these are pretty well covered in our typical classroom. But if we move over to the interpersonal side, this brings us into the realm of our Revolutionizing Engineering Department grant, the interpersonal. How do we create environments? How do we create graduates? How do we create laboratories that are inclusive and equitable? How do we help people develop empathy, to take perspectives? How do we help students understand self-presentation, conflict resolution, negotiation, teamwork, leadership? I think in our department, we probably are doing a better job than other departments in trying to take on this very, very difficult area, because we really do need to have students who are graduating who have these skills, these interpersonal competencies that will make them successful both on teams and as team leaders. And then finally, we get to the bottom, the intrapersonal. This is an area that is of particular interest to many people these days. Grit. What is it about certain people that have resilience and others don't? How does one grow grit? What about self-directed learning and flexibility, adaptability? What about ethics? What about perseverance? What about metacognition? All of these are incredibly important in terms of learning and being a successful learner. So these are all areas of interest, or should be of interest to faculty, and should be of interest to students as well in terms of growing their 21st century learning competencies. So here are some ideas for future Newsteader distinguished lectures. You would think I could spell my name right. Anyway, one, we continue to have to ask, what is the nature of knowing and knowledge? So for faculty members in the audience, or for students in the audience, or for anyone that matter, think about it. How do you know? What forms do your knowledge take? Is it generative? Are you able to transfer that knowledge from one place to another? There's a great paper written by some learning scientists that talk about learning to go. And the problem is, in many cases, it's not knowledge to go. It's knowledge for a particular setting, and then it's forgotten after the final exam. How do we learn or acquire that knowledge, and what are the best forms of mediation? How do we prevent the development of troublesome knowledge? How does knowledge and knowing change across disciplines, interdisciplines, and transdisciplines? Nancy and I were very interested in this when we started our work back in the early 2000s, because we said, how do you manage being an engineer, which is about simplifying and idealizing the world into a small diagram, and biology, which is about complexity and detail? How does one manage that cognitively? And then we have transdisciplines, which is the area that we felt that Eberhard and Melissa were working in, where you're trying to work across several disciplines, but you could never fully master more than two. So you had to figure out how to manage 2 or 3 or 4 disciplines simultaneously. And then finally, how can technology better respond to learner needs? I think we have to ask a question that all of us have just been forced to do online learning for a semester. I know for myself, I had a number of significant surprises, in many cases positive. If anyone had said, you're going to have to go teach online before this semester, I would have said, I'll retire early, because I just didn't really fully understand that maybe there are some possibilities when technology is mediating interactions at a distance. For example, just today, if 120 people are on this Zoom call, I can guarantee there would not have been 120 people in the IBB building, and they certainly wouldn't have been my relatives out in California, or Steve zooming in from Ireland. So I would hope that in the future, when you sit down and think about who do we want to come and talk to us, that you would exploit the research and knowledge across the 6 cognitive science domains. And maybe one year invite a neuroscientist who is asking questions about the human brain that are relevant to what we're doing in classrooms. And maybe the next year you will invite someone who is building intelligent tutoring systems that afford the possibility for personalized learning. And then the next year you would invite an anthropologist who would be asking questions about industry-based learning and how it's different from classroom learning. So with this, I want to end by thanking everyone who I've had the opportunity to spend 20 years with. Many of you, Ajit, Dawn, Joe Ledoux, Michelle. It's been a great ride. I can't imagine a better place to spend 20 years. I was given a ridiculous amount of freedom to do crazy, fun, innovative things. And we could never do it without the absolutely fabulous students that we've got at Georgia Tech that are going to be the people I miss the most. And with that, I thank you all.
Thank you, Wendy. Thank you very, very much. And I love the prescriptive ending telling us who we should, what areas we should be inviting. Wendy, you are going to be on one of our Newsteader lecture slides in the same way that you featured the people who were pioneers and shaped your thinking. You are a pioneer in our lifetime. And it was such a thrill for me to join our department because I came from the University of Pennsylvania, where your methods were adopted in problem-based learning in some of our courses. And so the idea to get to be in your orbit was a thrill, but I knew that you were no longer in the department. I knew that you were at the college level, and yet I came just at the right time when you really wanted to re-engage with the department. So it was such a special time in your orb because you had, when you went to the college, created and cultivated a community of scholars, not just in our department, but across Georgia Tech. So I walked into a setting where you were an inspirational, very patient teacher who had endless ideas that you then used us as your laboratory and your research subjects. And it was clear from today's lecture, as well as from people's reflections, that we're very grateful subjects and that you have transformed our lives. You have the ability of, in the moment, both studying us, but also helping us to understand what you're learning. And it's especially important because we like to have our subjects be blinded as to the experiment that they're participating in, but you actually have a way of giving us just enough information about why and what's your motivation of your study. And then to see your reflections about what you gathered after years of observation really helps us understand where you were headed, even more than we realized when we were subjects in the experiment in real time. And because I know that you're engaging in studies right now, I'm certain your life's work is not done, because these are studies that you still need to bring closure to, that you're going to look at that data, that you're going to then disseminate to the world about what you are finding out about the experiments that are right now, that are ongoing right now. And they are many. So I was actually, I think I'll say taken aback when I learned that you were going to be retiring. I felt a little bit afloat and like, where would we be going without you running way in the future ahead and telling us where we should be going? But I actually felt over these months, just what you shared, that you're shedding things you don't want to work on and retaining those things that you do. So as chair, I've thrown a few nuggets your way about things that I thought would be interesting to you. One of the reasons that on this plaque, we have the Whitaker building is because you were instrumental in designing those spaces. It is a learning space. And as we've now expanded our footprint quite a great deal to include a learning space, now a design space across the BioQuad, it gives us an opportunity to rethink the Whitaker building and how to create new designing spaces. And I know that's something that will draw you back to study and to participate in on campus. So I want to share that what you've heard here is a resonance. You're surrounded by people who love you, who believe in you, who are both in awe of you, but you help us feel part of your family. And it has been such a privilege to have this partnership. And I look forward to how that partnership will evolve in the future. Thank you. Thank you for what you've done. And thank you for the lives that you've touched. And thank you for agreeing to partner with us in the future.
Oh, yes, indeed, indeed. Thank you, Susan. I'm so humbled and honored, and this would not be happening without your thought and your desire to do this. So thank you so much.